Good day, everyone. For today, I am going to, or we are going to discuss the consistency of hyperbolic geometry. This is a collaborative task for final output. And first, I am going to discuss the inversion of punctured plane. By its definition, you can see in the figure na as a circle. So, fix a point 0 and a circle C centered at 0 or O of radius R. So, for a point P, ngayon yung makita sa illustration or sa figure, P such that, or O, the inverse of P is the unique point P on the ray starting from O and passing through P such that OP equals to R squared. So, the point in the figure O is called the center of inversion, and circle C is called the center or the circle of inversion, while R is called the radius of inversion. Okay, so other word, inversion is a transformation that involves taking a point in space and reflecting it through a fixed point known as the center of inversion. So the punctured plane is a plane with a single point removed, and the inversion of punctured plane involves reflecting all points is the plane through the center of inversion except of the point that was removed. Okay, so it is also defined that the punctured plane it is also known as the complex plane with the origin removed. So it is a fundamental mathematical object in complex analysis and topology. So inversion in the punctured plane, definitely it is a transformation that sends each point to its inverse with respect to a given circle centered at the origin. So more precisely, let's see be the circle centered at the origin with radius R, and let Z be a point in punctured plane. So then the inversion of Z with respect to C is given by the formula. So nani say formula. So Z prime is equals to R squared over Z plus B. So ang B diha is a complex number representing the center of the circle C. Geometrically, the transformation maps Z to the point Z on the line passing through the origin, and Z such that the product of the distance from the origin to Z and the Z is equal to the square of the radius R. Okay, so there are properties of inversion. So circular inversion, it is not a transformation of the Euclidean plane, since the center of inversion does not get mapped to a point in the plane. So however, if we include the point at infinity, we would have a transformation of Euclidean plane and this point of infinity. Okay, so the first properties of inversion is the theorem: points inside C map points outside of C, points outside map to points inside, and each point of and each point on C maps to itself. So the center of inversion maps to what we call this infinity set or null set. Okay, so for the theorem number 2, the inverse of a line through 0 or O is the line itself. So again, this is expanded by some of the mathematicians that this theorem, this should be immediate from the definition of inversion. However, note that the line is not pointwise invariant, with the exemption of the points on the circle of inversion. Perhaps more surprisingly is the next theorem. So ato ang tanawon ang next theorem. So naay figure, and then the inverse image of the line not passing through 0 or O is a circle passing through O. So naa diha ang circle which is O, then the radius, and naa siya the inverse image of a line not passing through 0. Okay, so ang P diha, so ato ang let P be the foot of the perpendicular from O to the line. So let Q be any other point on the line. So then P and Q are the respective inverse points. So ang P ug Q mo na sa inverse points nato no sa ato ang figure. So by its definition sa inverse points, OP equals OP is OP equals to OQ and OQ. So we can use this to show that OPQ is similar to OQP. Thus, the image of any Q on the line is the vertex of the right triangle inscribed in a circle with diameter OP. So, naay diameter nga OP, and then atong tan-awon og kanang ang OPQ similar bagyapon sa OQP. No, so with the help of theorem ato asiyang ma-prove, no. Okay, so muna siya. Other properties of inversion. So, theorem sa kini nga theorem, ingon siya nga, the inverse image of a circle not passing through 0 is a circle not passing through 0. So, makita niyo sa image nun, daghang mga points, mga lines, iyang center is 0 or O. Then, ay radius na A prime siguro ni, yeah, Q prime and then P prime. So, theorem number 5, the inversion preserves the angle measured between any two curves in the plane. So, that is, inversion is conformal. So, one of the proof ani nga theorem nga mo suffice is kining to case of an angle between line to the center of inversion curve. In the figure below, inyong makita ni sa next page ang figure na P ug ang Q are 2 points on a given curve P prime and Q prime are the corresponding points on the inverse curve. So, mao ni siya ang kining figure. So, ang kuan kuno, ang P ug Q kuno are 2 points on the given curve, and P prime and Q prime are the corresponding points on the inverse curve. So, P and Q 2 points siya. Unya ang iyang inverse mo ni siyang P prime o Q prime. So tan-aw nato, so mo ni siya P and Q. So inigbali na niya. So mahimo na siyang kining naay kini. Kini. Ana siya. So inigbali. So from gikan ani, so inverse ani is mao na ni siyang inverse kini. So naa na siya, no. Curve gihapon siya pero inverse na siya. So padayon ta, we need to show that M O P B is equals to M A P prime and D prime. So the sketchpad activity below which lead us to desired result. So inyong makita gihapon din no, na yung mga points diri sa ato ang next na slide. Okay, so the properties of inversion, next theorem is the under inversion, the image of a circle unsa maning orthogonal. Okay, so orthogonal di mo ni siya ang involving right angles, or it is statistically independent. So kanang kini di ang orthogonal, it is a lines or line segment that are perpendicular at their point of intersection. So two vectors are considered orthogonal if they form a 90-degree angle. So kung siya right angles din yung orthogonal. So or line segment ni nga perpendicular, no, or nag-intersect sila ba. Okay, so for the application of inversion, first let's look at the center of Apollonius. Center of Apollonius and inversion in the context of a magnet. So a common experiment is to place a magnet under a sheet of paper and then sprinkle iron filings on top of the paper. And then the iron filings are lined up along circle passing through points, the north and the south poles. So near the end of the magnet, these are the magnet lines of force. The theory of magnetism then studies equipotential lines. So this turned out that the circle of each which is orthogonal or right angles or a perpendicular na nag-intersect, this turns out that the circle of each which is orthogonal to all of the magnetic lines of force. The theory of inversion was created to deal with the theory of magnetism. So we can interpret this magnetic line of force and equipotential lines within geometry of circles. So overall, in in the application or in the conclusion of the inversion in the punctured plane. So it has many interesting properties, no, and applications. So for example, it is conformal transformation, meaning that it preserves angles and local shapes. So it is also useful for studying conformal maps of the punctured plane and for constructing circular backing. Okay, so next topic is the cross ratio and inversion. So the cross ratio and inversion are two concepts in mathematics that are related to projective geometry, and they are often used together to solve problems in this field. So, other words, the cross ratio is a mathematical tool that is used to measure the ratio of distances between four collinear points. It is also defined as the ratio of the products of the distances between the first and the third points and the second and the fourth points, divided by the product of distances between the first and the fourth points and the second and third points. So, muna siya, the inversion considered as the map of complex plane. The inversion also considered as the map of the complex plane onto itself. So it preserves the cross ratio up to preserves the cross ratio up to conjugacy. The cross ratio XYZW and XYZW prime, or I mean ang bali di ay sa XYZW, or ang inverse niya is X prime, Y prime, Z prime, and W prime are conjugate to each other. If one of them is real, then so is the other. Thus, the 4 points of the line or circle define a cross ratio preserved by inversions. So, what are the relationship between the cross ratio and inversion? So, the relationship between the relationship between the cross ratio and inversion can be used to solve many problems in projective geometry. So, this is applicable kung we will touch na sa projective geometry. So for example, if we have four collinear points and we want to find the cross ratio between them, we can choose a point on a line that is not one of the four given points, and then invert the 4 points with respect to this point. This will transform the line into a circle, and the cross ratio will be preserved. So we can then use the properties of the circle to find the cross ratio between the inverted points, and then invert the result to find the original cross ratio. Okay, so another application of the cross ratio and inversion in the study of circles and lines and projective geometry. So for example, if we have a circle and a line that intersects at 2 points, we can use inversion to transform the circle into another circle or a line. So gamitan nato inversion para mabali siya o mapurma gihapon nga circle or a line. So it will always depends on the location of its center with respect to the line. So tan-aw niya po nimo daghan niya pong mga considerations in applying the inversion of the points, no, in tan-aw ng location of its center with respect to the line. So by studying the cross ratios of the intersections of the original circle and line under images under inversion, we can derive many useful results about the geometry of circles and lines in projective space. So this is helpful in the projective geometry. Okay, so for the conclusion of the cross ratio and inversion, so these two are very important concepts in projective geometry. Ano man, and also they are very close or closely related. Because using the properties of this concept together, we can solve many problems in this field and derive many interesting results about the geometry of space. So, tungod di aning or gumikan aning cross ratio and inversion, gamit kayo ni siya sa projective geometry, kay we can able to solve problems in the field of projective geometry and derive many interesting results about the geometry of space. So, thank you everyone, and God bless us all.
Angular measure and inversions indicate that the image of an angle under inversion is never an angle. The point is that every angle in E to A has at least one side lying on a non-punctured line, and the image of a non-punctured line is always a punctured circle. Therefore, the following theorem doesn't mean it might seem to mean. So let's have theorem 1. If A and Q are non-collinear, then P prime equals if P and Q prime equals if Q. Then M angle APQ equals M angle AQ prime and P prime. So proof. Consider triangle PAQ and triangle Q prime A P prime. So, as you can see in the figure. So they have the angle A in common. Since AP prime equals A squared over AP prime and AQ prime equals A squared over AQ. So we have AP times AP prime equals AQ times AQ prime equals A squared. So that AP over AQ prime equals AQ over AP prime. So by the SAS similarity, or let's say a side angle side triangle. So triangle PAQ similar to triangle Q prime A prime. Note that reversal of order of vertices here, since angle APQ and angle AQ prime P prime are corresponding angles, so they have the same measure. So in the figure above, I mean in the side, P prime equals FP and Q prime equals FQ as before. Here we have U equals 180 minus alpha minus R equals 180 minus R minus A equals S minus A. Therefore, S equals U minus A. So the order of S and U depends on the order in which P and P prime appear on the ray. If P and P prime are interchanged, then we should interchange S and U. So getting U minus S equals A. Thus, in general, we have S minus U equals A. So let's have theorem 2. So under inversions, corresponding tangent angles are congruent. That is, if AB and AC are arcs with a tangent angle of measure R, then their images FAB and FAC have a tangent angle of measure R. So similarity for an arc and a segment, or a segment and a segment. Now, we have reflections across ill lines in the Poincare model. So we recall that the points in the Poincare model are the points of the interior E of a circle C with center at P. The L lines are: number 1, the intersection of E with lines through P, and number 2, the intersection E with circles C prime orthogonal to C. So makita ra siya sa figure. So if L is a hyperbolic line of the first type, then the reflection of E across L is defined in the familiar fashion as a 1 correspondence of E biconditional to E, such that for each point Q of E, Q and if Q are symmetric across L. If L is hyperbolic line of the second type, then the reflection of E across L is the inversion of E about C prime. To justify this definition, of course, we have to show that if F is an inversion about a circle C prime orthogonal to C, then FE equals to E. But this is not difficult to show. In the next few theorems, it should be understood that F is an inversion about C prime. C prime has center at A and intersects C orthogonally at R and S, and L equals E, not union C prime. So let's have theorem 1. FC equals C. Proof. FC is a circle. This circle contains R and S because FR equals R and FS equals S. By theorem 2 of the preceding section, FC and FC prime are orthogonal. But there is only one circle C which crosses C prime orthogonally at R and S. It is clear that P must be the center at any circle. Therefore, FC equals C. This was the required. So theorem 2. FE equals E. Proof. Let X be any point of E. Then AX intersects C at points T and U. Since FC equals C, we have U equals T and T equals FU. But inversions preserve betweenness on rays starting at A. Therefore, FTU equals TU and FXE. Thus, FE is a subset of E. We need to show conversely that E is a subset of FE. This is trivial. Given that FE is a subset of E, we have FFE is a subset of FE. Since FFE equals E, this gives E is a subset of FE. So we have theorem 3. Fm is hyperbolic line, then so also is Fm. M is the intersection E not union D, where D is either a circle orthogonal to E or a line orthogonal to C. Now, FD is orthogonal to C and is a line or circle, punctured or unpunctured. Let D prime be the corresponding complete line or circle. Thus, D then prime equals FD or D prime equals FD. Union A. Fm equals FD not union E, D prime not union E, which is hyperbolic line. We recall that hyperbolic angle is the angle formed by two rays in the Poincare model. So, the measure of general, we have S minus U equals A. So, let's have theorem 2. So, under inversions, corresponding tangent angles are congruent. That is, if AB and AC are arcs with a tangent angle of measure R, then their images if AB and if AC have a tangent angle of measure R. So, similarity for an arc and a segment, or a segment and a segment. Now, we have reflections across ill lines in the Poincare model. So, we recall that the points in the Poincare model are the points of the interior E of a circle C with center at P. The L lines are, number 1, the intersection of E with lines through P, and number 2, the intersection E with circles C prime orthogonal to C. So, makita ra siya sa figure. So, if L is a hyperbolic line of the first type, then the reflection of E across L is defined in the familiar fashion as a one correspondence of E by conditional to E, such that for each point Q of E, Q and if Q are symmetric across L. If L is hyperbolic line of the second type, then the reflection of E across L is the inversion of E about C prime. To justify this definition, of course, we have to show that if is an inversion about a circle C prime orthogonal to C, then FE equals to E. But this is not difficult to show. In the next few theorems, it should be understood that F is an inversion about C prime. C prime has center at A and intersects C orthogonally at R and S, and L equals E not union C prime. So let's have theorem 1. FC equals C. Proof. FC is a circle. This circle contains R and S because FR equals R and FS equals S. By Theorem 2 of the preceding section, FC and FC prime are orthogonal. But there is only one circle C which crosses C prime orthogonally at R and S. It is clear that P must be the center at any circle. Therefore, FC equals C. This was the required. So Theorem 2. FE equals E. Proof. Let X be any point of E. Then AX intersects C at points T and U. Since FC equals C, we have U equals P and T equals FU. But inversions preserve betweenness on rays starting at A. Therefore, FTU equals TU and FXE. Thus, FE is a subset of E. We need to show conversely that E is a subset of FE. This is trivial. Given that FE is a subset of E, we have FFE is a subset of FE. Since FFE equals E, this gives E is a subset of FE. So we have Theorem 3. Fm is hyperbolic line, then so also is Fm. M is the intersection E not union D, where D is either a circle orthogonal to E or a line orthogonal to C. Now, FD is orthogonal to C and is a line or circle, punctured or unpunctured. Let D prime be the corresponding complete line or circle. Thus, D then prime equals FD or D prime equals FD. Union A. Fm equals FD not union E. D prime not union E, which is hyperbolic line. We recall that hyperbolic angle is the angle formed by two rays in the Poincare model. So, the measure of hyperbolic angle is the measure of the angle formed by the tangent rays. We now sum up nearly all of the preceding discussion in the following theorem. Now, let's have Theorem 4. Let F be a reflection across E and hyperbolic line. Then, we have 4 conditions. Number 1, F is a one-to-one correspondence. E is to E. So, kay ba nam taaning one-to-one correspondence no kanang unique gani isara patan X and Y isara gid nga pares no one-to-one correspondence. So, number 2, F preserves the non-Euclidean distances between points. So number 3, F preserves hyperbolic lines. Lastly, F preserves measures of hyperbolic angles. So for hyperbolic lines of the first type passing through P, all this is trivial because in this case, F is an isometry in the Euclidean sense. It is therefore preserves distances of both types of lines, circles, orthogonally, and angular measure. For hyperbolic lines of the second type, conditions 1 to 4 follows from the theorems of this section and the preceding.
Going to recall the postulates or the axioms of Euclid's geometry. Infinitely, many lines can pass through any given single point. Only one line can pass through two distinct points. So proceed. The first postulate in the Euclid's Elements proposes that it is possible to draw a straight line from any point to any point. It means that one and only one line can pass through some given 2 points. There can be infinitely many pairs of parallel or perpendicular lines which can pass through a set of 2 distinct points. That 2 points are distinct determine a unique line passing through both of them. So as we can see on the figure on the screen, from right side, we are going to i-determine na to. So as we notice that the pair of parallel lines MA, so parallel lines MA, kani MA, and MB, kani ang MB, can be rotated by any amount. So also the locus of the point of intersection of a pair of perpendicular lines from A, any A and B here, A and B is a circle with diameter AB. Therefore, infinitely many pairs of perpendicular lines can pass through A and B. So, only the line L is a unique possibility. So, maoro ni siya. Ni L. Ni siya, line L is a unique possibility. Okay. Note, infinitely many lines can pass through a single point. 82 points in space always lie from a unique line. Infinitely many planes can pass through them. So 83 points in space always lie on a unique plane. So we're going to tackle these 4. The ruler postulate, bedwiness, plane separation, and angular measurement. So the axiom basically says that every line is a number line. So first we're going to tackle about the ruler postulate. The points of a line can be placed in a correspondence with a real number such that, first, to every point of the line there corresponds exactly one real number. Second, to every real number there corresponds exactly one point of the line. And lastly, the distance between 2 distinct points is the absolute value of the difference of the corresponding real numbers. So, we are always remember that the first and second conditions of the ruler postulate imply that there exists a one-to-one and onto function. As a reminder, we write the definitions for one-to-one and onto function. So, for every pair of points PQ, there is a number PQ called the distance from P to Q. So, for each line, there is one-to-one correspondence. F, point of line L to real numbers such that f of P is equal to x and f of Q is equal to y, then PQ is the absolute value of x and y, the value of the distance. So, from point L to R, we can correspond every point of the line to a real numbers. So, one-to-one correspondence is a bijection and can also be called onto. So, it means, so for example, it is the line L, and then we have here 8 points, 2 points. So consider that as a point. First point is the P and second point is the Q. So these 2 points of a line, and it is the numbers that corresponds to P, and also this number corresponds to Q. So the distance between P and Q is the absolute value of x minus y. Okay, continue. So we're going to move the topic betweenness. So one of the simplest ideas in geometry is that of betweenness for points on the line. Here we use the undefined term between to establish some properties of an order relation among points on a line and plane. So C is between A and B if A, B, and C are collinear and AC plus CB is equal to AB. So here, if A and B and C, A, B, C, A, and then C, and should B are collinear, and the distance from A to C plus the distance from C to B is the distance from A to B. So we're going to define the segment AB. The set containing A and B, segment AB. So the set containing A and B union the set containing all points P that are between A and B. So kani. And then again, we also define the ray. Ray AB this is the segment AB union the set of all points P such that B is between A and P. So, kani. Okay. Theorem. If P and Q are 2 points, then PQ is equal to QP. Second, PQ is greater than or equal to 0 and PQ is equal to 0 if and only if P is equal to Q. Okay, we're going to move the plane separation topic. For every line L, the points that do not lie on L form two disjoint non-empty sets H1 and H2 called half-plane bounded by L such that H of H1 and H2 is convex. And second, if P is in H1 and Q is in H2, then PQ intersects L. Convex are in H1 or H2, then all of segment P1 and P2 is in H1 or H2. So, imagine, we have here a line of L. Okay, so we have here H1 and H2. And then, as we can see, kaning ani o kini space sa H1 and H2 sa ubos is what we call the non-empty sets. And then, we have here a point, and point diri. So we called it A, P, and R. So kung ato na sila isa, that what we call the segment between there must intersect. The segment between there must intersect. Okay. So for the last, angular measures. Recall that an angle is the union of two rays with common endpoint. The common endpoint is called the vertex. The two rays are called sides of the angle. So the angle which is the union of the two rays OA and OB and is denoted as AOB or angle AOB. So as we can see on the figure on the screen, the angle AOB. So the interior of an angle AOB is the intersection of A, the half plane determined by the line OA which contains B, and the half plane determined by the line OB which contains A. So we can see it in the figure 1.6.2 below. And the interior of an angle AOB will be denoted by interior AOB. So the exterior of an angle AOB is the set of all points which are neither on AOB nor interior AOB. So the exterior of an angle AOB will be denoted by exterior AOB